Morning, morning. Am I audible? Okay. Okay. Good morning, good morning. So in online, syllabus is almost completed for this weekend and the phase test. Okay, so I think I was discussing mean free path. Mean free path, mean free time, that I have completed. Tell yes or no. Okay, okay. Degrees of freedom and everything I had discussed. Okay. So we'll discuss a few problems of the mean free path. Okay, then that will be this chapter will be over. Okay. So mean free path, we have discussed the formula. Lambda is the 2-3 formula I said. Remember? Okay. So suppose I am giving at STP velocity of gas molecule is 500 meter per second. Okay, at STP velocity of the gas molecule I have given 500 meter per second. Then find mean free path and mean free time, or they will say the average time between the successive collision. This mean free time means average time between successive collision. Okay, if diameter I have given diameter of molecule is equal to 2 angstrom. Okay, so at STP velocity of the gas molecule I have given 500 meter per second. Then we have to find the mean free path and mean free time or average time between successive collision if diameter of the molecule I give 2 angstrom. Okay. Then for the mean free path, which formula we will use? For the mean free path, which formula we have to use here? Because STP I have given, so we know the pressure and we know the temperature. Okay, number of molecule per unit volume we don't know. So what is the mean free path formula? Lambda is the 1 upon under root 2 pi d square into n. But this formula I cannot use because here directly I don't know the n value, number of molecule per unit volume. Then which formula you will use? N you will put P by kT. Remember last class I discussed N you can put P by kT. Say yes or no. Number of molecule per unit volume we got what? P by Kb into T. No response. Forget. What was the n here? Small n here. Number of molecule per unit volume. Number of molecule per unit volume. So if I have given this directly we can put, but I have not given the small n. So in the terms of pressure and temperature, how we can find? P by Kb into T. If I put here then lambda, what you will get? Kb into T will go up upon under root 2 pi d square into P. Now STP pressure you will put what? What is the pressure you will put? Tell fast. 1 atm. But like R value, K value we are using 1.38 into 10 to the power minus 23. K value 1.38 into 10 to the power minus 23 you will take. But K value, how I got 1.38 when I took the R is the 8.3. Remember, K value, we have taken R by NA. And R I have taken 8.3. How? Then when we are taking the R, we can take the R is equal to 8.3 when we are using the SI unit. Okay. So now here I have to put the pressure in a Pascal. So 1 into 1.01, or for the calculation we can take 10 to the power 5 Pascal. So pressure is the 10 to the power 5. Diameter already I have given. KB 1.38 into 10 to the power minus 23. STP temperature you will take 273. Then you will get the value of lambda directly. So this is 1.38 into 10 to the power minus 23. Temperature is the 273 upon under root 2. 1.4 you can write. Pi is the 3.14 into d square means diameter is 2 angstrom means 2 to the 4 into 10 to the power minus 20 into pressure I can take 10 to the power 5. Anybody will say what is the answer? Lengthy. Sir, change setting chat is for everyone. Why? So calculation you will do. That is a messages are coming to everyone. Okay. We will take the pressure in Pascal. STP pressure is 1 atm, but we have to put in Pascal. Why? Because we are lambda you will get in meter. After that maybe answer they are giving in angstrom or whatever. So we have to first find lambda in the meter. So if you are using the SI unit, lambda you will get in meter. Okay, and then maybe option are in the angstrom or in the micrometer you can convert. Okay, so pressure we have to take in MKS. So you will take what? Pascal. Pascal, that is a 10 to the power 5. Understood? 1.2 nearly coming. You will solve some 10 power something negative power you will get. 8 into 10 to the power minus 10. Okay. So approximation like 1 point, this you can write 1.4, this you can write 1.4, this will get cancelled out. Okay. And this you can take like 3.14, so slightly you have taken what? 91. Then 4 you can cancel. So approximate calculation you can do. And if they have given this type of calculation in the exam, so approximate answer we can check. Like this is the 1.38, this is the 1.4 you can take. 1.4 get cancel out. Here 3, suppose you are taking 3. Okay, so here 273 you can write 91. Now 91 by 4 directly you can write the answer. Means answer will be slightly close to that. Okay, and 10 power how we can find? Minus 23. This become minus 15. Minus 15 will go up plus 15. Okay, so when you will get 10 to the power minus 8. Okay. So approximately that angstrom. Yes. Okay. Okay. Everybody got? Okay then. So for options they will not give that much close, so that because they know that exact calculation will take time. So you have to check the 10 power, maybe some 10 power they will give different. Otherwise we can go through the approximation and we can check the options. Okay, which is the close option we can go. Okay. Next, how you will find the average time? So average time we will find by T average, that is a mean free time. It is a what? Time is the distance upon speed. So average distance upon average speed. What is the average distance? That is a lambda. And what is the average speed? VRMS or V whatever will take. So speed already they have given 500 meter per second. I said in the case of gas molecule, we will assume what? Gas molecules are moving with RMS speed. Okay. So average speed we take as a RMS. So time I want to find. Time is the distance upon speed. What is the average distance it is traveling? Lambda, that is a mean free time, mean free path. And VRMS already average speed they have given 500. Now lambda already you got, just divide it by 500, you will get the answer. Okay. 10 to the power minus 10 approximation, approximately you will get. Okay. Got it? Everybody will solve now? Okay. Next, suppose I am saying mean free path of a gas molecule is lambda, then find mean free path in x direction. Suppose I have given the mean free path of the gas molecule is lambda. So particularly I am asking what is a free path, what is a mean free path in the x direction? Lambda by 3. Immediately I got the answer. Good. Lambda by 3. Any other answer? So mean free path, I have given mean free path means it is traveling in a 3-dimensional space. So mean free path I have given lambda. So if they are asking like particularly this type of problem that what is the free path, mean free path in the x direction, then what you will say? Lambda by 3. Any other answer? Lambda by 3. Three lambda, okay. Lambda by 3. So just listen now. Mean free path, basically it is what? Between the average distance between the successive collision. Average distance between traveled in a successive collision. Okay, lambda by 3. Most of you are giving the answer lambda by 3. Just wait. Now listen. What I am saying, distance, like average distance between successive collision, that is called the mean free path. Okay. And the average time is the, we can say the relaxation time or mean free time. So suppose time it is taking t. Mean free time it is a suppose t. So in the time t, in the 3 dimension, how much distance it is traveling? Average distance it is traveling lambda. That is called the mean free path. In the average time, this average time is what? T. So in the time t, how much average distance it is traveling? Lambda. That I am asking particularly in the x direction. Okay. Just wait. Okay, so like suppose molecule moving 3 dimensions, so it is traveling the x distance, it is traveling the y distance, as well as it is traveling the z distance. Okay, total distance I have given what? Lambda. I am asking the particularly in the x direction. So distance means lambda x I am asking. Okay, lambda x is equal to what? Distance is equal to speed into time. Distance is equal to speed into time. Okay, so initial in the gas molecule mean free path I have given lambda. So lambda I can say what? VRMS into average time t average, whatever I am taking here. I can write or not, just I have used this formula. Lambda I can say what? Lambda is the distance. So average distance is the average speed into time. Average time between successive collision. Lambda, that is the average distance. It is what? Average speed into average time. Yes or no? I can write this lambda is the just previous problem I used the same formula. T average is the lambda by VRMS. Okay. Now I need lambda x, mean free path in the x direction. So lambda x I can write as VRMS or velocity in the x direction into time. It will take same. Why time same? Because in the time when it is colliding with any other molecule, average time, that is the same. Okay, in the same time it is traveling the lambda distance. I am asking only particularly in the x direction. Okay, this is okay or not? T average. Why I take the time same? Reason is what? In the two collision it is traveling the what? What is the average time? T average. In that total distance it is traveling lambda. I am asking in a x direction. Now if you remember in a derivation, if you remember, I said Vx square bar is equal to Vy square bar is equal to Vz square bar is equal to Vrms square by 3. Remember? Vrms square by 3. Suchita. Vx square bar is equal to Vy square bar is equal to Vz square bar is equal to Vrms square by 3. So what is the Vx you will get? Vx bar. Vx square bar is the Vrms square by 3. So what is the RMS speed in the x direction you will get? Vrms by root 3. Vrms by root 3. Getting my point or not? So this you will get lambda x is the what? Because Vx square bar is equal to Vrms square by 3. But I need the Vx. I need the Vx. So Vx what you will take? You will take the root on both sides. So root of velocity in the x direction is the root of this. Root of this what you will get? Vrms by root 3. Okay. Now this Vx you will put Vrms by root 3 into T average. Now you can say what is a lambda x? What is a lambda x? Vrms into T average is a lambda. So what is a lambda x? So lambda x you will get lambda by root 3. Okay. So similarly for the y direction or the z direction, all we can say lambda x is the lambda by root 3. Getting my point or not? Okay. Okay. Now right, next. If mean at 2 atmospheric pressure and 300 Kelvin, mean free time is 6 into 10 to the power minus 10 second, then find mean free time at 1 atmospheric pressure and 500 Kelvin. At 2 atmospheric pressure and 300 Kelvin, mean free time is 6 into 10 to the power minus 10 second. Then you have to find the mean free time of a gas at 1 atmospheric pressure and 500 Kelvin. Okay, so mean free time, what we can write? Mean free time, just I said, it is a lambda by Vrms. So we can say what? Mean free time, T average or tau you can say. T average, that is equal to what? Lambda upon Vrms. Okay. Lambda I don't know, RMS I don't know. Okay. But they are asking they have given one condition and they are asking for the other condition. So first I will find how the T average depends on the temperature and pressure. Okay. Which quantity it depends. So T average lambda formula we know that 1 upon under root 2 pi d square into n I can put P by kT, kb into T. This is a lambda formula. Okay. And Vrms I can say what? Vrms is the under root of 3 RT by M. Okay. Now for the given gas, D constant. R constant for all gases, molar mass constant, Kb constant, √2 constant, pi constant. So we can check the proportionality. So I can say that T average is directly proportional to. Now you can see pressure in the denominator under root T n to T. So what you will get? Root T by P. You can check. Rest of the quantities are constant. Kb constant, √2 constant, pi constant for the given gas, diameter of the molecule constant, 3r and m is constant. So here what is remaining? Under root T. Here what is remaining? T. So T upon root T, what you got? Under root T upon P. Yes or no? Everybody got? Now directly I can say what? T2 by T1, that is equal to what? Under root of T2 by T1 into pressure will get reversed, then you will get what? P1 by P2. Okay. I got the proportionality what? T average is directly proportional to under root T by P. Okay. Now T2 by T1 ratio of the time I can write as under root of T2 by T1 because directly proportional to root T and inversely proportional to pressure. That's why P1 by P2. Okay. Now T2 by T1, that I can say under root T2. T2 is the 500. T1 is the 300 into initial pressure I gave 2 atm, final pressure I gave 1 atm. Okay. Now this 0 and 0 cancel out. Then T2 what we got? T2 is equal to under root of 5 by 3 into 2 into T1 I gave 6 into 10 to the power minus 10. This up to this any problem anybody has? Tell fast. Okay. Now root 5 by 3 we can put what? Root 5 by 3 is the under root of 1.67 into 12 into 10 to the power minus 10. 1.67 root is what? So like 160, you can think about 167. 167 is the closer to 169. Minus 9.9. Listen. 1.67 root I need. So 1.67 means 1.69 is the square of 30. 169 is the square of 13. So 1.67 approximately we can write 1.3. 1.3 into 12 directly you will get the answer. So T2 you will get 1.3 into 12 into 10 to the power minus 10. Okay. Everybody got the answer or not? Okay. How root T came? Okay. So here you can see T. Here we are getting T and here is the root T. Okay. Now M, R, all are, this is the constant, this is the constant, this is the constant, this is the constant, this is the constant. Now what is remaining? T by P under root T. Okay. Now what is the proportionality you got? Under root T by P. Oppo, got it? Understood? Okay then. So this is KTG is over now. One more question that is on the internal energy I'll discuss. Okay. So you will say the answer. So if two gases are enclosed in container at temperature T1 and T2, and their degrees of freedom. If they are not saying the degrees of freedom, they are not given the data about the degrees of freedom, then we have to take what? We have to take the similar gas. If they are given the data, then we will consider. If they are not given, then we will take the similar gas. But I am giving here their degrees of freedom are same. If number of moles are N1 and N2, then find temperature of their mixture. If there is a no loss in energy anywhere, so if the two gases are enclosed in the container at the temperature T1 and T2 and their degrees of freedom are equal, if number of moles are N1 and N2, then we have to find the temperature of their mixture if we are considering no any loss. Okay. So 1 upon T1 plus 1 upon T2. It is equal to what? Suhas. It is the temperature. Final mixture temperature is the 1 by T1 plus 1 by T2. N1 T1 plus N2 T2 upon N1 plus N2. Okay, good. N1 T1. Okay, good. So in this case, what we will take? Total internal, no loss in energy. So total internal energy we will what? We will take as constant. So UI we can write as a UF UF is equal to UI. Now UI what I can write? Degrees of internal energy formula we have learned. 1 by 2 F into N1 into R into T1. 1 by 2 FNRT. Remember 1 by 2 FNRT. So for first gas number of mole is N1 and temperature is T1. For second gas 1 by 2 F N2 into R into T2. Okay. Final I can write as what? 1 by 2. Same gas, same degrees of freedom. So degrees of freedom you will take like diatomic you are mixing. So final mixture will be diatomic. Diatomic, so degree of freedom will remain same. Yes or no? Different gases you are mixing, son, then there is a problem. But here you are mixing the gas that has the same degrees of freedom. So you are mixing the F and F. So ultimately the degree of freedom will be F. Diatomic mixing, ultimately the mixture will be diatomic. Okay. So degrees of freedom you will take same. So 1 by 2 F into N. After mixing the total mole, what we will have? After mixing total mole, we have N1 plus N2 into R into T. Okay. Where T is the final mixture temperature. Now 1 by 2F, 1 by 2F, 1 by 2F cancel out. R cancel out. Now what is the T you got? N1 T1 plus N2 T2 upon N1 plus N2. This is the final mixture temperature. Okay. 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 So this is now over. Any doubt anybody has, then you can ask. Then otherwise I will start the calorimetry. So now I can start calorimetry. Okay. Okay, so in the calorimetry, we will discuss about the heat. When we are giving the heat to the body, what is the rise in temperature, and we will discuss about the state change also. So first, who will say the difference between the heat and the heat energy and thermal energy? What is the difference between the heat and sometimes we will use the thermal energy, like in the kinetic theory of gases. We have learned the kinetic energy of the gas molecule, that is a 3/2 kT. Okay, so that we call it thermal energy. Okay, and what is the heat energy? What is the difference between thermal energy and heat energy? So thermal energy is what? That like molecule has the kinetic energy 3/2 kT. This is due to the temperature. Okay, so due to the temperature they have the energy. So that energy is called the thermal energy. So energy of any body or energy of the molecule or on the gas due to the temperature, that energy is called the thermal energy. Okay, yes or no? And what is the heat energy? When the like heat energy transfer from one body to the another body due to the temperature difference, so that is called the heat. So what is transferring in the form of energy, that is called the heat energy. And heat like energy is transferring due to the difference of temperature. So thermal energy is the energy of the body or the molecule or the gas, whatever we are taking, is due to the temperature. That energy is called the thermal energy. And the energy that transfer from one body to the another body due to the temperature difference, that is called the heat energy. Okay, so like 3/2 kT we can say. Sir, one more time. What I am saying, what is the thermal energy? Thermal energy is the energy of any body or the object or the molecule that is due to the temperature of the body. That is due to the temperature. Like I have some temperature, my body temperature. So due to the temperature, what the energy I have, that energy is called the thermal energy. That energy is called thermal energy. Okay. Suppose one body temperature is more, other body temperature is less. Okay. When you put in contact, what will happen? Heat will flow, energy will flow from hot body to the cold body. So the energy that is flowing from hot body to the cold body, that energy is called heat energy. So energy transfer from one body to the another body due to the temperature difference, that energy is called the heat energy. Heat. And the energy of any body due to its temperature, that is called thermal energy. Like suppose one body you are taking, this is the 1, this is the 2. Its temperature is T1, its temperature is T2. Okay. So this body has some energy due to the temperature T1. This body has some energy due to the temperature T2. So this is the thermal energy. Okay. If I connect them, if I put them in the contact, so the energy will transfer from high temperature to low temperature. That energy is the heat. Okay. Okay, now, okay. So maybe you have learned also this heat given to anybody that is a Q is directly proportional to the mass of body. That we can do, we can verify it experimentally also. If you want to change the temperature of any body by the same amount. Okay, so suppose you are taking less mass, you will have to supply the heat for the small time. You are taking more mass, you have to supply the heat for more time. You have to supply the heat for the more time. Suppose constant rate you are supplying, X calorie per second you are supplying. When you are taking less mass, you have to supply the heat for the lesser time. When you are taking more mass, you have to supply the heat for more time. So we can say what? Heat supplied is directly proportional to the mass of the body, whatever we are taking. Yes or no? Means bigger mass if you want to heat and smaller mass. So in which case you have to supply the more heat, bigger mass, because you have to, if suppose you want to make the same temperature change for the small body and the large body. So if the mass is more, here mass is less. So if for the same temperature change, you will supply more heat, you require more heat for bigger body. Yes or no? So we can say Q directly proportional to M. Similarly, we can say Q directly proportional to delta theta. After combining these two, so Q is equal to M S delta theta. This formula maybe we have learned in the class 9th also. Where what is the S? S is the proportionality constant that we call what? Specific heat capacity. So Q is equal to ms delta theta. Delta theta is the change in temperature. M is the mass of the body. Change in temperature. So S is the proportionality constant, that is called the specific heat capacity. Okay. Yes or no? Everybody know this formula, I think. Q is equal to ms delta theta. Okay. Now, if you want to increase the temperature of the body, you have to supply the heat. If the body temperature is falling, it will release the heat. Means according to the delta theta positive means you want to increase the temperature. So you have to supply the heat. Q will be positive. When body temperature is falling means delta theta negative, it means heat is ejecting from the body. Okay. So S, we can say what here? S is the Q by M delta theta. From that we can say the unit of S. What is the unit of S? In the unit and dimension they can ask unit of any quantity. Means in the unit dimension we have not learned all the quantities. Why? Because that time we don't have the idea about all the quantities. But in our chapters, when the chapters are going on, when you are learning the new quantity, it is your responsibility. You have to find the unit and dimension of those quantities. Okay. So what is the unit of S? So SI unit we can say, or MKS unit. That is a joule per kg degree C or Kelvin, both you can use because it is a delta theta. So delta theta you can either write Kelvin or you can write as a degree C, it doesn't matter. Okay. Okay. What is the dimension? Dimension of S. So energy you will get ml2t minus 2, okay, upon m, and delta theta we write as a k. Now m and m cancel out, so what we got? L2t minus 2 k minus 1. Okay, so we got the unit and dimension of S. So how we can define the S? So we can define specific heat capacity by the amount of heat required. We can say if delta theta is equal to 1 and m is equal to 1, then we can say what? S is equal to Q. Okay, so what is the definition? Specific heat capacity is the amount of heat required, to raise the temperature of unit mass of a body by unit degree. I repeat again, specific heat capacity is equal to the amount of heat, S is equal to Q, is equal to the amount of heat required to raise the temperature of unit mass of the substance, by unit degree. Okay, so when m is equal to 1, delta theta is equal to 1, then S I can say Q. Okay, so amount of heat required to raise the temperature of unit mass of a substance by unit degree. Okay, got it? Okay, so one thing first we have to remember, when they are asking the heat corresponding to temperature change, when we require the heat corresponding to temperature change, always that heat we will take ms delta theta, whether it is a solid, liquid or gas. We will say the different thing, but formula we will use the same. Okay, specific heat we define different. So when there is a heat required to change the temperature of the body, so for the temperature change we will always use the formula ms delta theta. Mainly for the solid and liquid we can say, we will always use heat required is the ms delta theta. Okay, now S unit we got, S dimension we got. On which quantity S depends? So S is the proportionality constant. If you got that, S is the proportionality constant. So it does not depends on the mass of the substance. Whatever the mass you are taking, it doesn't matter, because more mass, more Q required. S will be constant. So S does not depends on the mass of the substance. It depends on the property of the substance. Okay, so it is the property of substance. Like suppose I am saying the copper will have its own specific heat. Okay, iron will have its own specific heat. Okay, but that also varies with temperature. Theoretically, in a problem we will take the specific heat same, but specific heat also varies with temperature. Okay, so we can say S is the property of the substance. And it depends on the what substance you are taking and what is the temperature. So it is the property of the substance and it depends on the which substance we are taking and what is the temperature. Understood? But theoretically, for any substance, we will take the specific heat is constant. Okay, but if they are asking the theoretical like optional theoretical question, in a numerical problem we will take the S constant. But if they are asking S depends on, so it depends on the substance and temperature. Understood or not? For ideal gas, it won't depend. Ideal gas, we define the different specific heat, that is, we define molar heat capacity, and for molar heat capacity will depends on the process. Like we will learn the CP, CV, so many different process, different molar heat capacity you will learn. So for the gas, we will discuss later on. Getting my point or not? So it depends on the process for the gases, how you are changing the temperature. CPCV, if you remember. Okay. Understood or not? Okay. So we can say what? S is the property S depends upon substance and temperature. Okay. Okay. Which substance has the maximum specific heat capacity? Which substance has maximum specific heat capacity? Water. So water has more specific heat capacity. Okay. Okay. So who will say, suppose I am saying I have the two substance. Okay, one substance specific heat is lesser, one substance specific heat is more. Okay, for this, when I am supplying the same heat, when we are supplying the same heat, whose temperature change will be more? I have the two substance. One has the less specific heat, other has the more specific heat. If I am supplying the same heat, whose temperature change will be more? Less specific heat substance. Yes or no? So whose specific heat is lesser, its temperature change will be more. Yes or no? Okay, this everybody got, because from the mathematical formula also we can say, because whose S will be more, whose S will be less, its temperature change will be more, delta theta will be more. Understood? So water has the more specific heat. Water has the more specific heat means if I have the water and any other substance. So water has a more specific heat. So suppose I am supplying the equal amount of heat in water and the substance. So water temperature will change lesser or maximum. Water has the more specific heat. So if water I am taking and any other substance I am taking, I am supplying the same amount of heat. So whose temperature change will be more? Water or other substance. Water temperature change will be lesser. Why? S is more for water. S is more for water. Yes or no? So temperature change will be lesser. Okay. substance temperature change will be more. That's why when we want to eject the heat from somewhere, some like nuclear power plant, we want to eject the heat, extra heat we want to eject. So we use the water as a coolant. Why? Because when the more amount of heat will pass in a water, then the temperature change of the water will be lesser. More amount of heat will pass, so comparatively to the other substance, change in temperature of the water will be lesser. Otherwise, suppose other substance we are taking, that become more heated, so it will create the problem. That's why we use the water as a coolant, because when we are supplying the heat to the water, change in the temperature of the water will be lesser in comparison to other substance. Got it or not? That's why water we use as a coolant. Understood or not? Why? For the same heat, change in the temperature in a water will be lesser in comparison to the other substance. Okay, so that's why water will not get heated more. So that's why we can use more heat we can pass for the water, so that water we can use as a coolant. Okay, that's why water can be used as coolant. Okay, so by using the common sense, you will say, suppose I have the one wooden material, any material I have, and metal I have. So metal specific heat will be more, or wood specific heat will be more? Or suppose non-metal I have, metal and non-metal, whose specific heat will be more? Metal, non-metal, metal, wood, metal, non-metal, metal. Metal, by the common sense, suppose you pass the heat in an iron rod and suppose any fiber or any plastic body. So when you pass the heat, equal amount of heat, which body will get heated more? Metal or the plastic body? Metal will get heated more. Metal get heated more means same amount of heat. Metal get heated more means specific heat of the metal has to be lesser. Yes or no? Okay, so metal will have the lesser specific heat in comparison to the non-metal. Got it? So that's why when you pass the same amount of heat in metal and non-metal, so change in the temperature in the metal will be more. Okay, that's why we use the so suppose in the cooking food we use which metal we use. Why? Because metal will absorb the heat, and for the equal amount, some amount of heat, temperature change will be more in the metal. So their specific heat is less, so their change in temperature will be more, so they can get heated up to the more temperature. Okay, so suppose I am saying utensils, we prefer what? High specific heat, low conductivity, high conductivity, low specific heat, high conductivity, high specific heat. What the answer you will say? We prefer to make utensils, we prefer high conductivity, high specific heat, low conductivity, low specific heat, high conductivity, low specific heat, like 4 permutation combination we can make. Low specific heat, high conductivity. Good. That is the answer. High conductivity, lesser specific heat. Lesser specific heat, why? Because when we pass some amount of heat, more temperature change, it will get more heated, so it will transfer more amount of heat to the food. Okay, so low specific heat is required. And high conductivity, why? Because most of the heat it will transfer to the food what you are cooking in that. So high conductivity, low specific heat we require to make the utensils. Okay, now completed. Okay then. So one small question you say. Suppose you have the two bodies, that is the 1 and 2. They are the identical bodies. They are identical body. One body is at the temperature 0 degrees C and other body is at the temperature 100 degrees C. Okay, we have the two identical bodies. We have the two identical bodies. One body is kept at the 0 degree C, other body is at the 100 degree C. Okay, and specific heat capacity is directly proportional to temperature. Specific heat capacity of the body is directly proportional to the temperature. More temperature, more specific heat capacity. Okay, so in the body 1 and 2, which will have the more heat capacity? In body 1 and 2, which will have the more heat capacity? 2. Why? 2 is at the higher temperature. Specific heat capacity is directly proportional to temperature, so 2 will have the high specific heat. Other term like mass, density, everything they have equal. They have the equal property, but their temperature are different. That's why their specific heats are different. Okay. Now I put both bodies in contact. So their common temperature, because the heat will flow from hot body to the cold body till their equilibrium will come. Okay, till their temperature become equal. So their equilibrium temperature will be equal to 50, less than 50, greater than 50. Their equilibrium temperature will be less than 50, greater than 50, equal to 50. You have to say 50. Okay, 50, greater than 50, more 50, less than 50. Okay, less than 50, equal to 50. Okay, control. Okay, so suppose I am saying specific heat is independent of temperature. Specific heat is independent of temperature. Then if I am putting them in contact, then what will happen? Then answer will be 50. If we are putting in contact, their specific heat does not depend on temperature. Their specific heat is constant. Then answer you will get 50. Why? One body will give the heat, other body will take the heat. This will give the heat, this will take the heat. At equilibrium, their temperature will be equal. Okay, that equilibrium temperature I am asking. Okay, so if I am taking the specific heat is same, if S is same at all temperature, then this will give the heat, this will take the heat. How much heat it will give? So heat given by 2 is equal to heat taken by 2. Okay, taken by 1. Okay, now first I am saying when the specific heat is same at all temperature, means specific heat does not depend on temperature, then I am saying the answer first. Okay, so if specific heat is same at all temperature, so heat given by the body 2 will be heat taken by the body 1. Suppose final temperature is, if final temperature is equal to theta. Okay, so 2 will give the heat. So it is going from 100 to theta. It is coming from 100 to theta. Then how much temperature change? Delta theta, you can say 100 minus theta. So in that case, you will get heat given by 2. ms delta theta, you will say what? 100 minus theta. This is the heat given by the body 2. What is the heat taken by body 1? ms into, it is at 0, now it reached to the theta. So how much temperature change? Theta minus 0. Initially 0, final equilibrium temperature is the theta. So how much increase? Theta. So theta minus 0, what we got? This. Okay. And second body is falling from 100 to theta. So how much temperature change? 100 minus theta. If I am taking specific heat same, then ms and ms I am writing both sides. So ms and ms cancel out. So you got the 2 theta is equal to 100. Then theta you got 50 degree C. In that case, equilibrium temperature is 50. When they are saying the both body has the specific heat equal, it does not depend upon temperature. Yes or no? Greater than 50. Okay, now you corrected the answer. Okay, this answer when you will get, when they are saying the specific heat of both body are equal. Are say yes or no? Okay. Okay, so answer will be 50 when specific heat are equal. But I am giving what? Specific heat capacity is directly proportional to temperature. Okay. So here specific heat I cannot take same. In this problem, specific heat I cannot take same. Okay. Then what we will do? Then answer will not be 50. Okay. So more than 50 or less than 50 I have to check. Without doing any calculation you can say. Without doing any calculation you can check the answer. How? So one body is giving the heat, other body is taking the heat. Okay. Same equal amount of heat transfer is there. One is giving, one is taking. So equal amount of heat exchange is there. Listen carefully. Equal amount of heat exchange is there. Okay. One body is taking heat, one body is giving the heat. So equal amount of heat exchange. So when the Q same, so we say that delta theta will be more. Delta change in temperature will be more, whose specific heat is less. First digest this statement. I just repeated that. I just said this statement. Same heat when we are passing. So whose temperature change will be more? Whose specific heat is less? Which body specific heat is less? This everybody understood or not? If equal amount of heat you are passing, so whose temperature change will be more? The body which has the lesser specific heat. Okay. So by using that, this and this, in body 1 and 2, which body will have lesser specific heat according to the problem given? Body 1 has the lesser specific heat. Why? Its temperature is less. So its temperature is less, so its specific heat will be lesser. Whose specific heat is lesser? Its temperature change will be more when same amount of heat is passing. So body 1 temperature change will be more, body 2 temperature change will be lesser. Okay. So suppose final temperature is the theta. Final equilibrium temperature is theta. Then we can say change in temperature of the body 1 means delta theta 1 will be greater than delta theta 2. Yes or no? Delta theta 1 will be greater than delta theta 2. Yes or no? Because body S1, because S1 is less than S2. Body 1 specific heat is lesser than body 2. That's why I can say temperature change will be more in a 1 with respect to, in comparison to the 2. Okay. Now delta theta 1, what you will say? Theta minus 0. That is greater than what? 100 minus theta, because body 2 temperature changes from 100 to theta. So what is the change? 100 minus theta. Body 1 0 to theta. What is the change? Theta minus 0. This understood or not? Okay. Now 2 theta greater than 100. So theta what we got? Greater than 50 degree C. So means final equilibrium temperature will be greater than 50 degree C. This is the without using any calculation. From the logic you can directly say theta is greater than 50. Yes or no? Okay. Second way, if you want to do more mathematically, then you can say what? Suppose one is the change in temperature delta theta 1, other change in temperature is delta theta 2. So heat given is equal to heat taken. So you will say what? M1 S1 delta theta 1 is equal to M S2 delta theta 2. Ravindra. Okay. So what I said here, body 1 and 2, they are identical in all aspect, but their temperature is different. Their temperature is different, so their specific heat is different. Why? Because in the problem they have given specific heat is directly proportional to the temperature. So whose temperature more, its specific heat will be more. Okay. And we have learned when we are passing the equal amount of heat for the same heat exchange, the body which has the lesser specific heat, its temperature change will be more. Like metal and non-metal, you have to remember in the mind. Metal has the lesser specific heat, that's why its temperature change more for the same heat exchange between metal and non-metal. Ravindra. Okay, so which material, which substance has the lesser specific heat, its change in temperature will be more when we are passing the equal amount of heat. Okay, this statement you will remember. Which metal, which substance has the lesser specific heat, its temperature change will be more when we are passing the equal amount of heat. So whose specific heat is more? Body 2 specific heat is more. So that's why its temperature change will be lesser. Why? Here heat exchange are equal. One is giving the heat, other is taking the same amount of heat. Okay. So that's why I said change in temperature in a body 1 will be more because its specific heat is lesser. So delta theta 1 is greater than delta theta 2. From that we got this calculation. Okay. Second way, what I'm saying, heat given by the body 2 is equal to heat taken by the body 1. So M1, MS1 delta theta 1 is equal to MS2 delta theta 2. Now here, if I find the ratio S1 by S2. So S1 by S2, what I will get? Delta theta 2 by delta theta 1. Okay. Now S1 is the specific heat of body 1, S2 is the specific heat of the body 2. Which is more? S2 is more. S1 is greater than S2. So this quantity, you will say what? S1 greater than S2. So this quantity will be less than 1. Are say yes or no? S1 is lesser, S2 is more. Then S1 upon S2 less than 1. Then I will get what? Delta theta 2 less than delta theta 1. Delta theta 2 is what? 100 minus theta is less than theta minus 0. So again you got what? 2 theta greater than 100 or theta we can say greater than 50 degree C. Okay. So there are two ways there. You can do by any. Okay. So that statement you have to remember, whose specific heat is lesser, for the same heat exchange, its temperature change will be more. Okay. And metal has the, that's why metal has the more temperature change. That's why metal we can take, it has a lesser specific heat. Okay. Okay then. And all these specific heat, you know, specific heat of the water in the CGS unit is what? Unit also important, 1 calorie per gram per degree C. Specific heat of water, 1 calorie per gram per degree C. But in MKS, suppose they have given the heat exchange in the joule, okay, mass they have given in the kg, means we are following the MKS. So this we cannot use. So in the MKS we'll use so 1 calorie is equal to 4.2 joule. Okay, so this will be the 4.2 joule. In the place of the gram we have to take the kg. Okay, so gram you can write as a 10 to the power minus 3 kg. Minus 3 will go up, so it will become plus 3. So then what you will get? 4.2 into 10 to the power 3 joule per kg per degree C. So if you are using the MKS unit, then specific heat of the water you will not put 1. Okay, you will take what? 4.2 into 10 to the power 3. Somewhere we give the 4.18 also. Okay. Everybody got or not? So when we are calculating like heat exchange, they have given in the joule, masses they are given the kg. So we have to take the specific heat of water is what? 4.2 into 10 to the power 3 joule per kg per degree C. Okay. Specific heat of ice 0.5 calorie per gram per degree C, or in that we can write as 2.1 into 10 to the power 3 joule per kg per degree C. Okay. And third one is the S of steam, that is 0.47, but in the numerical problem most of the time we take as a 0.5. Okay, so 0.47 into 4200 joule per kg per degree C. Okay then. Okay. So this is about the specific heat and the one formula Q is equal to ms delta theta. Okay. Now next quantity is the thermal or heat capacity. previous slide. Okay. Okay, so thermal or heat capacity. So symbol we can use like a specific heat capacity, we can use small s, thermal capacity we can use the capital S. Okay, so heat capacity and the specific heat capacity, both are the different. Here heat capacity or the thermal capacity we defined as dq by dt or d theta, whatever you can write. Temperature we are writing, so d theta we can here. Okay, dq by d theta. dq by m into d theta is the specific heat capacity. When you are taking the per unit rise in temperature for a unit mass, then it is a specific heat capacity. But when we are saying the heat capacity only, so heat capacity is defined for heat required for the unit temperature change. Heat required for unit temperature change. So heat capacity heat required for unit change in temperature okay. So heat required for a unit change in temperature for a unit mass of a body is specific heat capacity. Heat capacity or thermal capacity is the heat required to raise the temperature by unit degree. Okay, so like suppose I have given the heat capacity is the x, heat capacity of any body is x. So to change the temperature of the body by 50 degrees C, how much heat required? Heat capacity of any body is x. To change the temperature of the body by 50 degrees C, how much heat required? 50x. Why? Unit degree, how much heat required? Heat capacity. So heat capacity I have given x. Now directly I have given the delta theta is what? 50. So how much total heat required? 50 into x. Okay. Because heat we can say heat capacity into delta theta. So unit of heat capacity, that is we can say joule per degree C. Okay, similarly you can find the dimension also. And heat capacity we can say what? That is equal to what? Q upon delta theta. Q is equal to what? Q upon delta theta. So Q we can say what? Ms delta theta upon delta theta. So delta theta cancel out. What is the heat capacity? So you can say what? M into S. So heat capacity is the product of the mass of the substance and specific heat capacity of the substance. Heat capacity is equal to the mass of substance into specific heat capacity of the substance. Okay. Yes or no? So don't get confused between the heat capacity and specific heat capacity. Otherwise, sometimes in the problem we have to decide by the unit. Okay, if they are giving the joule per gram per degree C, it means they are talking about the specific heat capacity. If they are saying the heat capacity using the heat capacity, but they are giving the unit as a joule per gram per joule per kg per degree C, it means that is a heat capacity they are saying, but it is a specific heat capacity. So sometimes you have to focus on the unit also. Okay, understood? Everybody got or not? Okay. Okay, so one problem just do on this. Find ratio of heat capacity of two sphere of radius ratio 1:2, density ratio 2:3, and specific heat capacity ratio 4:3. Then find the ratio of heat capacity of the two bodies, two sphere. If their ratio are in the radius in the ratio 1:2, density in the ratio 2:3, and the specific heat capacity are in the ratio 4:3. So specific heat, suppose I am saying heat capacity I am writing as a small c. Okay. So I can say what? C1 by C2, that is equal to what? M1 S1 upon M2 S2 by the formula of the specific heat capacity. Mass they have not given, but the density and the radius ratio they have given. So mass I can write as volume into density. Volume you will say sphere volume is 4/3 pi R1 cube into density rho 1 into S1 upon second mass you can say what? Volume 4/3 pi R2 cube into rho 2 into S2. Now 4/3 pi cancel out, R1 by R2 whole cube. R1 by R2 we got what? They have given 1:2. So what you will get? 1/8 into density ratio they have given density ratio 2:3. Then you will get 2:3. And specific heat ratio what they have given 4:3. Then you will get 4:3. Now 4 to the 8, 8 cancel out. What you got? Ratio is the 1:9. This type of question already they ask in the NEET. Okay. Okay, so this weekend syllabus is over also. So and this calorimetry is not in the weekend syllabus. Up to the only KTG is the syllabus. Okay. So if required, then I will take the class on Friday. Otherwise, we'll see. Okay. Okay, then bye bye. QR code. Okay, bye bye bye. Number I will give and the live classes will stop. Then after that you can ask. Okay, I will send the number. Okay. Okay, 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 bye bye. What happened? Write online exams. Okay, that all queries came after that. The online problem. What is the online problem? From which side I have to go? No, you have to register here. They will add your number and then you can appear in the online exam through the app only. Okay, so who is going to take the second class? So just say, ask them to add your number. Give your number. Okay. Okay then. Bye bye.